Hi, Lauren. So I'm going to attempt to help you with part B of the question that we were talking about. It's quite difficult to do it over a screen because we really need to think in 3 dimensions. So you'll have to bear with me. I'm going to try and annotate on the diagram as best as I can, and we'll see how we go. So you can see in this question, at the moment, what we have is a square coil with a gap. So you should be able to see a gap here. And so what that means is when the conductor, which is the coil itself, falls into the magnetic field, an EMF is induced. Okay, that's the rule. If a conductor is moving relative to a magnetic field, we get an EMF induced. An EMF is just a voltage, which when you're thinking about electrical circuits, it's what gives the electrons the push. It provides energy to electrons in order for them to move around. But for current to flow, we have to have a complete circuit. And in this case, we don't. So in part A, all you were finding was the value of the voltage that gets put across this square coil and nothing to do with current flow. It's only in B where the coil becomes a continual loop. So we fix this. And so a current would be able to flow. Now, what you need to think about is as it falls, it's falling through a magnetic field. And so a voltage is set up. And now that is going to cause a current to flow. When a current flows, it sets up its own magnetic field. Okay, and we use our right hand grip rule. So we thumbs up, curl our fingers round to check the direction. So let's take a look in this case what we actually have. So what we have is a force down due to gravity. Okay, so I'll label this as FG. Okay, so this thing is physically falling because it's got a mass, it's in a gravitational field, so it's falling due to gravity. We know that we have movement of a conductor now inside of a magnetic field, and we've got that into the plane of the paper. We're going to generate a current, so we're going to use our right hand grip rule. Okay, so first finger is our field, so that's pointing into the screen. The force, which is my thumb, needs to point down towards the ground, okay, because that's gravity. And so hopefully you can see then that the current flow in the coil is going to go in, let me change my color pen, in a direction like this. Okay, so that's just using our generator rule. We can now use our right hand grip rule again to look at the direction of the magnetic field that gets set up inside that coil. So remember, if we've got current flow going radially, we will have a magnetic field coming through the center of that coil. And we know if we align it with the coil current direction that I've just put on the picture there, we know then that the field is coming out. And we know that the north pole is our thumb and the south pole is the soft bit of our hand. And so the north pole, if I try and draw it in 3D, I want you to imagine that this is in and out of the page, but obviously I can't draw that. What we've got is the magnetic field set up like this. So it's going to be north on this side of the coil, and it's going to be south underneath. Okay, so north closest to you in front of the coil, south behind the coil, but obviously I can't draw that. Now we also know that the magnetic field that was already set up is going into the plane of the paper from north to south. So what we now have is once this coil is inside of the magnetic field, what we actually have is a coil that is falling where this north pole of the magnetic field, because of the current, is going to be falling on top of the north pole of the original magnetic field. Norths and norths repel. Okay, so there's going to be repulsion between these two. Additionally, this south is falling on top of this south. Okay, and so what we're going to have is repulsion between the north and the north and the south and the south. Now, this magnetic field down here is already fixed. The coil is falling down The repulsion then is going to be up. Okay, so there's now a force due to the two magnetic fields interacting, acting up, and that's going to act on the coil. Okay, we're getting repulsion from this North Pole on the coil in the upwards direction. And so now what we have is a magnetic force acting against the gravitational force. And so the resultant force that is acting down on the coil gets smaller. Okay, so the total force is now going to be the gravitational force minus the magnetic force. So the force that is causing this square coil to fall and accelerate down is actually smaller now. And so because it's accelerating at a lower rate, we're now going to be taking longer to get down to the bottom of the page. Hopefully that makes sense. Let me know if it doesn't.